Hello, it's Keith here, and this is lesson 17 of the Chibiakumas series of my Z80 programming tutorials. Now, we've been looking over the last few weeks of this series about how the CPC and the Spectrum draw their backgrounds. We're going to move on to the MSX this time, because while the MSX has a very similar looking background, it's actually drawn in quite a different way, and the reason for that is what works well on the CPC is impossible on the MSX, and what works well on the MSX is not possible on the CPC. The reason is the screen of the CPC is part of the conventional memory, so the Z80 can write to it using the push command usually, but on the MSX it's controlled by the VDP, and the VDP is much slower pixel for pixel than the CPC with its push command. So we have to do things differently and manipulate the advantages of the MSX for the MSX screen, so although it looks the same, it's actually very different. Now, in the same way as on the CPC the screen is drawn in different sections, that's also true on the MSX. The MSX gradient and the blank areas and the tile areas are all drawn separately. However, the way it works is quite different to the CPC, mainly because the VDP is drawing the tiles and the blank areas, and it does a multi-processing trick. While the VDP is busy drawing those areas, the Z80 will actually use direct memory access and start drawing the gradients. So it's quite tricky the way it does it, and that's how we managed to get the MSX to be as fast as the CPC, even though if we'd only used the VDP it would have been slower. Today we're going to start by just looking at the tile map areas. So that's this area here, and the ground area here. So we're going to look at that code and we're going to see how it works. Let's just have a very quick look at the game in action so you can see the gradient and the parallax scrolling. So you can see the different areas scroll in different speeds, and in this case we're scrolling from the right to the left, but the game can scroll in the opposite direction as well. So I think the first thing we want to do is have a look at how the tile strips are stored in the VDP's memory. Now, we're going to use the debugger for this because this shows us the way that the screen is actually stored in RAM. Now, the VDP is only showing 192 lines of the screen visibly here, but the actual internal memory is a total of 1024 lines in total, and this is split up into 256 line chunks. Now, if I just change this here, and we set this to page 0, you can see this is the first screen buffer, and it looks like this one is still being drawn here, but then you can see there's some Chibico sprites down here, and these are using the spare area. If we just need to change this to 256, now we can see all of them. So you can see that we've got the Chibico and the Botchan sprites here, and these are in the unused area of the first 256. Now if we go to the second 256, this is the visible screen buffer, so this is this showing here, and we've got the start of the sprites here. Now I believe this is bank 2 of the sprites, but if we go further down a bit more, you can see here we've got the tile map. Now this is being used to draw these buildings here and also the ground here. You can see them as tile strips here. Now they use the entire width of the screen within the virtual memory, and that's important because for the way that this is drawn, and you can see they're all in a common block at a fixed Y position, and the Y position is actually calculated by the loading routine, but this is where they're actually stored in memory. And if we just go to the final page, you can just see all of the remaining sprites here, and even the font at the bottom here. So this is how they're laid out in memory. Now you don't need to know too much about that for today's example, but you do need to have a bit of an understanding of the fact that these appear at a Y position within the VDP memory, because you will see that within the code we're going to look at today. So we'll just get all of this out of the way now, and we'll start having a look. So let's have a look at the actual code and see how it works. So here's the code we're going to be looking at today, the background tiles routine. Now when this is executed, it's passed a set of parameters. Now here is the template of what you will see when we actually define the backgrounds and start them drawing. We're going to start drawing the tile map first and then the gradient, and the order is important. We have to draw the tile map first because the tile map actually initializes the gradient routine as well. The gradient routine on the MSX2 actually doesn't draw the gradient. It's a bit of a misnamed function. It actually fills the blank areas, but the gradient is drawn while the areas are filled and the tile map is drawn. So that's why it's important we do the tiles first. Now when we execute the tiles, we pass it 3 variables. The first one is the definition of the gradients. We're not going to look at that today. That's done by the Z80. And then we also pass in HL the MSX2 tile definition, and in DE we can pass a V9K tile definition. The reason we pass 2 definitions is the level code is common for the V9K and the regular MSX2, but the actual code that handles this routine has compiler definitions and is different depending on the system we're running on. So that's why we're using 2 different variables to pass 2 different definitions. The code is actually the same that does both. The only difference is the V9K version is much more complex, has much bigger tiles, because the V9K is so much more powerful and has so much more memory. Now let's start actually having a look at the code. So when it comes to the tile list that we pass in DE and HL, the definition is structured like this. Each line has a starting Y offset, and this is from the top of the screen, a number of lines that the tile is going to be drawn. Every tile is always the full width of the screen. That's a requirement of the code. Now we have a Y offset of the tile. You'll notice this is a word, so it's 2 bytes. This is the Y offset within the VDP memory, and it's stored as an offset from the start of the tile map. So our tile map in this example is actually part of the sprites. So we are effectively an offset from this point here, and this point is calculated and self-modified in by the loading of the level code. Now the one here is just an example, and we've got it set to 10, but it would actually be at 0 within the real example. But you can see this will actually be the offset, and then we're actually adding the height of the previous tile to the following offset to calculate the position of the next tile down, because they are all in consecutive order here. Now after that we then have a tick mask. We've got this thing within Chibiakumas, as I've mentioned a few times, called the ticks occurred, and this is a bit that will be either 1, 2, 4 or 8 and things like that, and this allows us to make events happen every tick, every other tick, every fourth tick, etc. And so this bit mask defines which ticks the background will scroll, and so we're defining here the clouds will move very slowly, the ground will move very fast, and the buildings will move somewhere in between. We then have an extra byte here which is used as a control byte. This is modified automatically by the code, and it remembers the current offset of the scroll position. So we just always leave that 0. Now one interesting thing is the top bit here actually has an alternate purpose. If this is 0, then the scrolling will be reversed. Usually it goes from the right to the left, but if we set this to 0, it will go left to right. Now during this routine we're going to be setting various data into this command definition that we're going to pass to the VDP. So we've got these various source, destination and number definitions here that define the area we're copying from and to. Now this is the true start of the background tile code once we've passed this definition to it. You'll see that there's a compiled definition loaded in here. If we're on the V9K, HL and DE are swapped around, and that means we're going to be using the DE definition rather than the normal HL one. On the MSX2 we then set ILY to 0. ILY is used by the gradient routine, so we have to do this first to initialize the gradient routine. We're not going to look at the gradient routine today, we will look at it later though because it's very important. So what we do first is we're loading in the screen position of the currently loading screen. The visible screen will be the other one, of course. This is modified automatically by the screen flip routine. We then load in the Y offset we're going to draw to, and we replace the loaded in definition with that because the screen will always be at 0 or 256. The screens are always 256 height in the virtual memory, even if they're visible 192, you see. So now we've loaded the destination location in completeness. So now we load in the tile height from A, and we load that into the tile definition here. We only need to set a single byte here. The tiles are always only a few pixels tall. You have to keep them small because even though the MSX2 VDP can draw these things relatively fast, it's not that fast, so we have to make sure the tiles don't cover too much of the screen. Now we load in D and E, and this is the offset of the tiles within the definitions of the sprites, and we then add the offset of the tiles, and this is self-modified in as the tiles were loaded by the loading routines, and this now means we've got the correct source Y location for the data. Next what we do is we are checking bit 7 of the bit mask. As I said, that will allow the scrolling to reverse, and we are then doing our shift accordingly here. We're using some self-modifying code here. We're either setting this to an inc HL or a dec HL. We're going to see where that occurs later. Now one thing to notice is on the Turbo R we're actually slowing down the background scroll routine here. This will be done via self-modifying code, but normally we're working in pairs here. Next what we're doing is we're loading in the ticks occurred, adding in the tick mask, and if the result is 0 we're not going to do a scroll. If it isn't 0 then we are going to do a scroll. Now you've got 2 no operations here, but when this actually executes in memory these will be a pair of dec HLs or a pair of inc HLs, or possibly just one depending on the system, and that's been done by this self-modifying code here. So when we get to this point, we've got the source X in memory. Now I do need to explain how we are in concept drawing the tiles. Let's have a look. So as I said, the tiles are a strip in memory. Now what we're doing is, if you think about it, we've got a full width 256 tile strip that will fill the entire width of the screen, and we want to make it appear that that's scrolling. And because the VDP works fast, if it does big copies, we want to copy big chunks of memory. So what we do is we set a scroll position. This starts at the far left and it gradually moves across in 2 pixel chunks on the MSX2, because the MSX2 has to work in 2 pixel pairs, effectively in bytes. And then what we would do is we will copy one chunk to the far left hand of the side of the screen, and then we will copy the opposite chunk to the right hand side of the screen. And because the position that we split those 2 chunks increases, this gives the appearance of a scrolling effect, and it only means we're copying 2 chunks. So it's fast, it looks like a good scrolling effect, and it works all round. The only disadvantage is we do need a full 256 pixel wide strip within our memory, but that's just the price we have to pay for the speed, and the speed is an important factor on the MSX2. We could have done more crazy things on the V9K, but the MSX2 isn't that fast, to be honest. So that's our concept. So we're loading in the source X from the current offset within the tile that we're drawing. We're then inverting that, and that will define the number of pixels we're drawing. If you think of it here, if this is the source X, then this is the number X, and then we're copying that here. So we've now defined the number of X. We're copying these to the far left of the screen, so we're setting the destination X to 0, and we're also setting the top bit of number X to 0 as well, and we'll see why we do that in just a moment. Now we're loading in the HMMM definition. This is the definition of the data we're going to draw. What we do now is we check if the number X is 0. You see, there will be times where we need to fill a full 256 pixels of the tile in one go if the scrolling has fully reset effectively. And we've got a special routine called byte up that does that. All it does is it sets the top byte of NX to 1. Usually we only work with a single byte, but in this case we need to work with both bytes. It's a special case that only happens one time in every 128 or 256 ticks. So that's what we do there. Now on the V9K we just do a fast copy with the LMMM busy check, but on the MSX2 we have to be cleverer. We run a command called busy gradient. We're going to look at this later in another lesson. What it does is it checks if the VDP is busy. If it's not, it immediately returns. If it is, it starts using the Z80's processor to use direct memory access and start drawing the gradient while the VDP is busy. You see, while the VDP is drawing tiles or fills, the Z80 can still access the memory without causing any problems. So that's what we're doing to get our speed up. So the busy gradient command will be filling the gradient with the Z80 until the VDP is not busy anymore. At that point it will back up all its status and it will return. Effectively what we're doing here is a multi-threaded command. We've got the VDP processor and the Z80 processor doing commands together, and the Z80 is waiting for the VDP to finish to give it another job. When the command returns here, we are able to do that other job, so we tell the VDP to fill the first part of the tile map. We've now effectively filled this part here, and so what we need to do now is fill this part here, and you'll notice that the way we calculate this is from the far left up until the split point here, and that's exactly what we do here. So now we set the source to 0 and we load in the number that we filled last time, which will be this lot here, and that effectively denotes this point here. And so we load that in as the destination this time, but it's possibly 0. If we did that byte up command here, we will have filled all 256 in one go. So we're just checking if there's nothing to draw here and skipping if that's the case. Now once we've defined the starting position, we now flip the bits, and that defines the number we're going to copy. So this time we're effectively copying this width here. So once we've worked out the destination position, we now flip the bits, because this will now define the amount that we actually need to fill this area here. And so now what we do is we store that in the number of X that we want to fill, and we now run the busy gradient again, once again filling with the Z80 any gradient while the VDP is busy. Once the VDP is no longer busy, we now do this draw here, and then what we do is we repeat here, going back all the way up to here, and this will keep repeating until we get a tile height of 0 here, which defines the end of the list, as you can see here. So that's effectively how it works. Now this routine is, as I say, common to the V9K and the MSX2. It's pretty complex. It took me a lot of time to get it working right, mostly because I'm an idiot with maths and things, but it does work really well. The tricky thing is the busy gradients. We're going to look at the busy gradients later. Next time we're going to have a look at the flood fill command, which does the blank areas of the background, and then we'll look at the busy gradient as well. And finally, we'll look at the V9K gradient, which is drawn very differently. One of the reasons for that is on the Turbo R, the Z80 commands are actually slower than on the MSX2, which is a bit odd. But the V9K can do a much simpler way of filling the background, so we use that on the V9K, but we do have to play around a bit on the MSX2. Anyway, I hope you've enjoyed this week's lesson. Please like and subscribe as always if you did. Thanks for watching today anyway, and goodbye.